Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thank you very much for coming to the second day on time. As you can see, some people are still a little bit groggy. I bet it was a good party last night. Sorry I missed it. I'm Dave Malton. I'm going to be talking today about problems and solutions in enterprise network control, moving on to motivating what we call the 4D architecture. So we've talked a lot over the past couple of days about isolation, this notion of trying to isolate users from each other. Now, what my takeaway from looking at lots of different routing designs of different kinds of networks is what network designers really want to do is they want to deal in groups. They basically want ways of bagging users and hosts together, and then they can say, all right, I want to measure all the traffic from this group, or I want to restrict the people in this group to only go to some set of resources, or only talk to each other. Or I now want to control the QoS of traffic in sort of that group of users or hosts. But now achieving this today using typical routing designs, the things that are available, results in horrible spaghetti messes. I mean, what tools are available? Things like VLANs. You go into the layer 2 Ethernet switches and you plumb in these basically virtual circuits between all the hosts, or actually the ports, that you want put together into a group. You do very clever IP address assignment. You do things like say, okay, I'm going to assign all my servers that are very secure from this address block, and then I'm going to put packet filters everywhere to only let certain hosts get into that address block. Or it might even do crazy things. It's like, okay, multicast enabled hosts, they get even IP addresses. And ones that shouldn't, things that shouldn't get multicast, they get odd IP addresses. I mean, you see these kinds of very strange things, basically, because that's what you have to do if you want to use the tools that routers give you today in order to create these groups and then measure and control traffic among them. Basically, we think it's important to let designers configure policy in terms of groups. They shouldn't have to worry about these sort of, is it a layer 2 thing, a layer 3 thing? Do I use VLANs or this OSPF configurations? Let them think in terms of these groups. That's what they want to talk in terms of. Another big problem is that device configuration is a nightmare. I mean, when people talk about device configuration, this is what they're talking about. This is just a few excerpts, just a few fraction of a percent of a lines from a router configuration file. And I don't expect you to read it. The only takeaway I want you to have is this is really low-level grotty stuff. You have to go to every interface on your router and you have to say your IP address is this, your subnet mask is this. You are a serial point-to-point interface on this port, on this slot, and again, here's your IP address. Here's the type of IP access group that I want you to apply. Basically, the packet filters, number 143, should be applied to all packets arriving on this interface. And here's the definition of packet filter 143. Packets from this IP address should be denied. Ones from any other IP address should be permitted. I mean, this is the level of grot that people have to do. And there's a huge amount of it. So if you take this is a graph showing the number of lines of configuration file for each router in a network, a reasonable size network. It's got about 100 routers in it, broken out by the different types of functions served by each of those lines. You see, whoa, this fairly small network with 100 routers has tens of thousands of lines of configuration file, doing lots of fairly sophisticated stuff. There's lots of stuff in there. This AAA stuff is all about things like NAT, or it's regulating sort of which packets are allowed to go through. There's lots of policy in there. There's lots of configuration on interfaces, lots of commands to say exactly which of these packet filters or policies apply to each of the interfaces in the box. And there's this huge chicken or the egg problem, because before I can roll out my network, I have to put configurations onto the routers, right? Once I roll it out, I can make changes to the router configurations over the network. But if I make a mistake, the router drops off the network, and now someone has to physically go to that router in order to log in manually on the console and fix the configuration. This is a very common thing to do if people have ever configured routers. The typical thing is you're changing some packet filter that guards access to the router, and you accidentally include the IP address that you happen to be logged in from. You apply the packet filter, and wham, now the router is filtering off all packets coming from you. Basically, our notion is that we want to have zero device-specific configuration on all routers. It should be possible to put the routers out in the field knowing nothing other than a security key for the network that they're supposed to be part of. And it should then be possible to basically push out configurations to those routers reliably under any situation, regardless if there are problems in that configuration. You always want to maintain some type of control channel to each of the switches that are going to be distributed physically in space. Oops. There we go. Another thing that we see a lot is that network designers want to do these things that sound relatively simple. They sound like very sane things to do, but achieving them is actually very hard in practice. This is a picture of, it's actually based on Microsoft's data center, but it's pretty typical for a lot of data centers. Basically, there's some big sort of core-facing routers up at the top that connect into the rest of the corporate network. Then there's another layer of basically load balancing routers. Then there's another layer called access routers along the bottom, and a whole bunch of servers that are connected directly into these access routers. And the reason this is done is for load balancing purposes and reliability. If you notice, these access routers all have two links up into sort of the distribution layer, and the distribution layer is very well meshed into the core layer. Right? Now, what a designer typically wants to do is they want to say, all right, I'd like traffic coming in to be load balanced, going to server, load balanced nicely over all of these links. All right? There are two links to each access router, and I'd like traffic going to that to sort of use all of those available paths. Now, achieving that is pretty hard. If I use Ethernet, well, Ethernet is going to compute a spanning tree over this. It's basically going to ignore most of the links in here, and in fact, I will use at most one link to each of these access routers. I can switch over to OSPF and do something called equal cost multipath, but that basically means I have to particularly choose the weights on these links such that all paths to the routers that I want them to go to, all paths to each server, have exactly the same OSPF metric. So I have the choice of either trying to do load balancing or traffic engineering. I can't do both at the same time. Another little graph widget that shows up a lot is this kind of butterfly. These are typically used when I'm connecting sort of two parts of my network together, maybe the access part of my network over here and the core part of my network over here. And again, the notion is relatively simple. I want to be able to survive any single router failure. Okay? Now, what I'd like to have happen is if, say, this link here fails, well, I'd like the traffic from this router to, say, go around this way to get to this router if it then has to go out on those links. However, when you actually build one of these things, it turns out it's incredibly difficult to configure it correctly so that you avoid this. Your packet sort of taking this Z-shaped thing through there. Now, explaining the details of why this is would take too long. But again, there's this very simple thing that, you build this widget, it's obvious what you want to have happen. But actually configuring routers to do it is very hard. We'd like to be able to support customized behaviors. There's also this notion of embracing heterogeneity or dying. So no two router versions have the same capability. A Cisco 7500 is a very, very different beast than a Cisco 12000. This is why they have different version numbers. And even, in the same network, there will always be devices with different capabilities. Now, in part also, device vendors add features to differentiate their products. No one wants to be making a commodity box. And so if your notion of management or control is that you're going to sort of take each router and treat it as a generic, an instance of some generic class which has abstract methods on it like install route, you're going to be stillborn because the device vendors aren't going to support you. To have a working system, you have to have ways that your management and control system can leverage all the cool features that they've put into those boxes, right? To basically take advantage of their differentiation. They have to work with the vendors. It's okay to have sort of if there was a common format for configuration state. XML or something, whatever, standard data representation stuff. That's okay. But you can't have a one-size-fits-all logic that computes what the state should be on the routers. Here's our notion of what we should do. We're basically in a world today where there's a whole bunch of stuff that happens in what's called the management plane. It's basically, analysis tools and whatnot that produce router configuration files, basically settings for BGP and OSPF and Ethernet and RSTP and whatnot, that actually run in real time on the routers. And as a result, packet filters and forwarding tables get produced and pushed down into the data plane. Our notion is that there's huge amounts of redundant logic here. And the language that's used to sort of express what really goes into the data plane is just very convoluted to figure out what you need to put in the top so that the right forwarding state gets put into your data plane. Our notion is instead, let's get all the decision-making logic lifted out of the routers and instead put into what we call the decision plane. Our notion is to go for a RISC router, sort of what would a reduced instruction set router be. Now, if we're basically going to lobotomize the routers, we need to install a very robust nervous system, which we call the dissemination plane, that'll connect the servers that implement the decision plane with the routers, which are still distributed in space, doing the data plane. So this is sort of how it looks. And this is what we call the 4D architecture. There's a decision plane where all decisions about what should happen in this network are made. Down at the data plane, where packets are actually forwarded, we model that as a set of tables, things like a forwarding table, a packet filter table, or whatnot. And the decisions made by the decision plane are shipped down to the routers by what we call the dissemination plane. It is that very robust nervous system. Now, in order to sort of feed the decision plane with the information that it needs, the switches among themselves run this fairly simple protocol we call the discovery plane, whereby they figure out who their neighbors are and what the bandwidths are, how much memory each of them has, what the capabilities of each device are. And then that information is moved through the dissemination plane up to the servers that implement the decision plane. Now, how would this actually work? How do you use this? Well, you install a security key on each device in your network. You connect them together. And then you connect a number of these decision elements, the servers that implement the decision plane, around the network, and then off it should go. So I mean, basically, Notion, here's a bunch of switches connected, 45 together. We've added 5 decision elements around the outside. We use more than one for robustness. These decision elements are basically replicas of each other. One fails, another takes over. And now we go. So you might have lots of questions about, does this actually work? Are there reliability problems? How long does it take? Are there scalability issues? One word answer is yes. A nice thing about the 4D is we designed it so performance can be predicted. Basically, before you deploy your network, you can say, here are the parameters of my network. Here's sort of the maximum propagation delay across my network. This is the number of routers. What will my reconvergence time be? And you can look at that number and say, yeah, that's good enough, or no, that's not good enough, and then you know you need to do something else. Today, with OSPF, it's very hard to answer those questions. Will adding another router to my network cause some other router to run out of memory? I don't know, connect it and see if your network crashes. That's what you have to do. There are very few predictive models. We also found that 4D does enable this customized decision logic. So if we take this kind of tree, we actually set this up with real devices running real traffic, and we control it with RSTP, that's an Ethernet spanning tree protocol, rapid spanning tree, and we control it with the 4D, we basically find that you get much higher throughput, on average, with 4D than you do with RSTP. Why is that? It's basically because RSTP has chosen a very inefficient tree. It's sending all traffic to S6 so that all 3 flows from these hosts at the bottom to this router up top have to go along this one path, and this becomes the bottleneck. The 4D logic, still relatively simple, just moves it around. Right? Basically, what we're also illustrating here is that there's no notion of this is a layer 2 solution or a layer 3 solution. The 4D basically can implement both, right? Because when you sort of abstract out to these tables, they're the same. Now, things that we're interested on, sort of motivated by some of the conversations here and some of our other thinking, is we got to tie the hosts and the users back into the network. Right? So we've been talking about the network so far. And the 4D basically gets us back to that happy land that I think Mark Pepping talked about, where every Ethernet jack on the wall is effectively the same. You could take any host and plug it in anywhere, because the routers themselves have no configuration on them until the decision element pushes out configuration to them. So they're all sort of omnipotent. They can all have any set of features or any host connected to them. But now we do need to differentiate those ports based on the host or the user that's connected into it. How do we do that? Effectively, we need to extend the 4D into the host at least a little bit. You could imagine working the following way. The 4D creates paths between newly connected hosts and some authentication server. I mean, Martin talked about this as part of the Ethane Insane work. And then basically the host can bootstrap users log in, and now discovery plane between the switch and the host can find out what is actually out there on the other side of the port. And now routes can be pushed out to the switches, and host policy can be pushed out to the host based on the identity of that host or the identity of the user who's actually logged into that host. Things like your DNS, your IPsec policy, all that goop. Now, we also think of 4D as being a very interesting framework for network control. Basically, we'd like the decision plane to be modular and extensible. So for example, and going back to that notion of isolation, we'd like each group that the network designer has created to want to be able to create or sort of specify the decision logic that should be used for controlling connectivity among the members of that group. So there'll be multiple groups, sort of multiple decision logics provided by different people that all get slotted into this decision plane, and it should all work itself out. We also need to support device heterogeneity again. We'd like it to be the case that when vendors sort of ship a new box with some new feature, they can also just ship some decision logic with it. You shove that into your decision elements, and now your decision elements know how to take advantage of that cool new weighted fair queuing, Uber, deep packet inspection, whatever capability that's built into the box. So sort of our grand vision is that the 4D is basically going to become something that can arbitrate access to resources. It becomes very much kind of like the operating system mentality again. These decision logics, there are resources in the network. The different decision logics might want to make conflicting decisions about how those resources should be used or applied or accessed. And the 4D layer at the lowest levels of the decision plane are going to have to arbitrate among those, just like an operating system. Now, our first step towards this grand vision is that we would like to make 4D the easiest framework in which to implement and sort of cool routing and network control ideas. Basically, what Click did for routers, we want to now do for the network. Click made it very easy, the Click modular router framework, made it very easy to sort of take a VLAN forwarding table and some weighted fair queuing stuff and plug it together so you could play around with different capabilities in the data plane. We want to make a very easy framework so that anyone who wants to can shove in some decision logic and see how it would work and use the 4D architecture to do that. Thanks. Questions?
Very quick questions. How do the decision elements maintain consistency among themselves?
Okay, so the model that we're currently using is relatively simple, which is basically strict replication. So each of the discovery plane that I talked about, that information is delivered to all the decision elements. So they all have up-to-date information. And then we use, in this case, a master election protocol so that there's only one who's actually writing configuration state down in. We're also, that's what we do today, and it seems to be scalable and work for up to, sort of 1,000 router networks. What we're looking at is kinds of hierarchy. Our notion here is that the 4D isn't going to take over the whole internet, not all at once. I mean, each enterprise that can define a policy for itself. Basically, each administrative domain would run a single instance of this 4D.
Okay. And it's sort of the same question in the way that now so if router I begins to use the such and such an output of decision elements and is talking to router J, do we know that router J is also in possession of the same level of?
So one of the things that we're experimenting with is actually different dissemination plane consistency models. So the simplest one is to do what basically OSPF does today, which is immediate insertion. So you compute some new result, you just put it into your table immediately. Now we can implement that simply in the dissemination plane by saying the decision element sends out the data to two different routers. They install it as soon as they get it, and there's the potential for short-lived forwarding loops until both updates land. The other thing you can do is imagine basically having a time-based synchronization where you say, okay, receive the update, don't apply it until time X, and you put time X far enough in the future that they'll both have it. So now you're down to sort of clock synchronization granularity. And then the third possibility is you could actually imagine going up to sort of full kind of, not ACID transaction semantics, but a much more rigid where, you go to each switch, you have the update, now commit. But that's...
I can imagine, the world will continue to be buggy, right? And so there's going to be a day when you'll produce a decision plane decision which some router will claim is faulty and other routers will accept, particularly because you have a heterogeneous world of routers. So something can be faulty just because you don't realize that this is a Cisco such and such lacking upgrade 6, right?
Yeah.
And so it'll say, something's wrong. I blue screen when I install that.
Yeah.
Right? And so you're going to need a way to back out, or you're going to get system use.
So my answer to that question, and I think that's a very excellent point, and very interesting research to be done there. But my current answer is with my engineer hat on, which is that that's a relatively uncommon, likely to be a relatively uncommon occurrence, and my proposal is we should accept sort of the forwarding inconsistencies that happen when that does. So basically, the updates will be applied to all the switches that take them. The one that won't take it says, wait a second, I can't do this. And now the network is in an inconsistent state for 50, 120 milliseconds while the decision element goes off and computes a more acceptable state and pushes it out. But like I say, that's an engineering answer. But for real networks, it seems like that's good enough. Because reconvergence times today are 300 milliseconds, a second, 5 seconds.
Ken, I think you sort of really nailed the problem, given that in the distributed system community, people have studied this problem for a long time. But sort of, if you look at the state of art in today's distributed routing, which is a distributed algorithm, there has no consistent state, any of the semantics you're talking about anyway. So the fact is, I think I would sort of, I think the first claim I would say is that there's no worse than today. If anything, it's better because we can discover things actually didn't work, and there's a central resolution point to so recover from it. So I think again, sort of the question here is, can we build stronger semantics consistency in this kind of routing protocols? I think that's an excellent direction to go. And
Yeah, I think it's interesting.
So I have a dumb question. If routing has no consistent state, how come we verify it using a checksum across the route group?
No, consistent way. Fred, I think when I say inconsistent, meaning that you want to sort of, we have the whole thing converges, right? We have this concept called there's converge, meaning that's where the consistent means that
So for,
expecting some other.
so for example, there people have looked at even with OSPF, right, which uses floods LSAs. It's possible for two routers to basically install new routing tables at different times, such that there is a short-lived forwarding loop between them. And the Sprint people have gone out and they've measured this, and some of the people who've worked there now have a proposal for how you could add more logic to OSPF to try and prevent these kinds of things in some situations. But OSPF today doesn't. It says, oh, short-lived routing loops, yeah, that's okay. Reconvergence is 100, 300 milliseconds. That's good enough.